When attempting to solve a second-order linear differential equation, that is, one that involves the second derivative, and when it's non-homogenous, that means on the right-hand side we don't have 0. What we need to do is to find two things. We need to find the particular integral, the complementary function, YCF. We need to find YCF, the complementary function, and we need to find the particular integral. So we'll call that YPI. So YCF is your general solution, and YPI is your particular solution, your specific solution. So we're going to use the left-hand side to find the general solution, YCF. So first, what we want is something called an auxiliary equation. And we do that by converting this into a quadratic equation. So we use the coefficients of the first and second derivatives of y. So I can rewrite this as the second derivative. Let's write it out like this. So y double prime plus 0 times the first derivative minus y equals. Now, we're only interested in the left-hand side of this equation. Okay, so all I've done is I've written that as y double prime, and I've written that as it is, and I've inserted this just to show that there is a coefficient of 0 multiplied by my first derivative. So if I wanted to turn that into a quadratic auxiliary equation, it would be lambda squared plus 0 lambda minus 1 equals 0. So I'm looking at these coefficients. So this coefficient of 1 and that coefficient of 1. So that now is my auxiliary equation. And you can solve that really easily. So lambda is equal to plus or minus 1. So I can say lambda 1 equals 1 and lambda 2 equals negative 1. So these are my two solutions, and I'm going to use those in order to write an expression for my complementary function. Right, so YCF, for when you have two real roots, let me just write that out. So I have two real and distinct roots. So I can write YCF as A times e to the lambda 1 x plus b times e to the lambda 2x. Now this is a standard form for when you have two real and distinct roots. So I'm just going to substitute lambda 1 and lambda 2 in there and write an expression for YCF. So YCF is A, which is unknown, times e to the 1 times x, plus b, unknown, times e to the negative 1 times x. So that's my complementary function there, YCF. That forms half of my solution, because after I found YCF and YPI, my final answer is going to be the sum of the two. So y is going to be YCF plus YPI. So I'm going to find this and add it to YCF. So we found YCF. That's what we did just now from the left-hand side of the equation. Okay, so to make this really clear, I'm going to split my page into two, just to show that we're working on different sides of this equation. So I use the left-hand side to find the complementary function. I'm now going to work on the right-hand side. So let me just draw a line down the middle there. Okay, so working on the right-hand side, because what we have is a linear expression, I can start with a linear guess at ypi. So I can say ypi is probably linear, something like cx plus d. And it doesn't matter what names you give these coefficients, a, b, c, d, p, or q. You'd not use a or b because we've already used a or b, a and b here. So I'm choosing the next two letters of the alphabet. All right, so that's my form for my particular integral, but I'm going to need the second derivative of that. So let's differentiate ypi twice. So the first derivative of a linear function is just the coefficient c. So the derivative of cx is c. The derivative of d is 0 because it's a constant. And then the second derivative is the derivative of this constant here, which is 0. So now I have my first and second derivatives. I can rewrite this. So I'm going to take this expression and substitute the derivatives we just found. So I'm going to take that and I'm going to substitute the second derivative 0 in there. And I'm going to substitute my expression for y in there. Hopefully I'll be able to solve for c and d. So I'm going to say 0 minus brackets cx plus d equals 2x minus 1. So you notice how cx plus d is my y. I put that there. That's there behind that negative sign. So if I multiply by -1, that gives me negative cx minus d equals 2x minus 1. Now, if you look at the coefficients, you can use the coefficient for x to figure out what c is. So if I look at the coefficient of x here, it's just 2. And the coefficient of x here is negative c. And those two have to be the same. So if negative c is equal to 2, so if negative c is 2, then c has to be negative 2. And similarly, if negative d is equal to -1, then d has to be equal to 1. So I'll write negative d is equal to -1, so d must be equal to 1. So now we know c and d. We can write our particular integral because that's what we're trying to find. So I'll just I'll copy this, and I can now write my particular integral as cx plus d. So that's -2 in there and 1 there. So ypi equals -2x plus 1. So now we have ypi, my particular integral, and I have my ycf, which is my complementary function, the general solution. I can say my final answer is the sum of these two. So if I bring this down here, now I have my two solutions. I can say the final solution, y, is equal to ycf plus ypi. So YCF is this, and YPI is that. So I can say Y is A, an unknown constant, times e to the x, plus B times e to the minus x, minus 2x, plus 1. And that would now be your final solution to this non-homogeneous second-order linear differential equation. So I found both solutions and I've added them together. I still have these unknown constants, but that's fine.